Hi, my name is Karen Ye, and I will present our work, Linguistic Structure as Weak Supervision for Visual Scene Graph Generation, joined with my advisor, Andriana Kowalska. Scene graphs are a structural graphical representation of an image. It can be used in image retrieval, visual question answering, and so on. At the core of the scene graph generation is recognizing the visual entities and inferring their relations, namely object detection and visual relation detection. Although the scene graph is a holistic representation of an image, the way to learn it, aka the types of supervision models use, only focus on local information. For example, the fully supervised scene graph generation maps local visual regions to labels without requiring the model to understand the whole image. The current weakly supervised scene graph generation task also uses local information. In its task formulation, each text triplet is just a local representation of the visual scene, thus causes ambiguity. So our study aims to understand the image in a holistic framework, and we propose to use captions as supervision. The benefits are threefold. First, captions capture global context. They may describe entities that are shared in multiple different relations. Second, captions are linguistic construct. Thus, the language sequential ordering provides common sense regarding sensible triplets. Third, the cost of gathering paired caption is almost free, since we can mine the descriptions paired with images on the internet. We summarize our contributions here. First, we propose an approach that leverages global context, which captures the information across triplet. We call this global context phrasal context, and it enables more accurate representation of the text concepts. Second, we modeled sequential context to reason about common sense relations. It is similar to a language model and prevents nonsensical triplets from being generated. Finally, we adapted the iterative detection method from weakly supervised object detection, which proves spurious relations between caption words and image regions. Here is an overview of our model. Our model uses the image's paired caption as weak supervision to learn the entities in the image and the relations among them. At inference time, it generates scene graphs without help from text. To learn our model, we first allow phrasal context information to propagate on the text graph to enrich the entity word. Then, based on the contextualized text feature and the visual proposal fast RCN features, we optimize a text-guided attention model to provide the image-level entity prediction and associate the text entities with visual regions best describing them. We use a joint probability to choose boxes associated with both subject and object. Then use the top scoring boxes to learn a better visual text association. Finally, we use an RNN sequential model to capture the vision language common sense and refine our final predictions. We use visual genome and MS-COCO datasets in the experiments. The VGGT graph setting is a simplified setting, which we use ground truth text graph annotations. The reason for this setting is that it helps to isolate the contribution of global context from the noises in the captions. In VG-CapGraph and COCO-CapGraph settings, we use text graph parsed from real captions. We test our model on two visual genome test splits. Xu's split is more frequently used in comparing fully supervised methods, and the Zarian's split has members from weakly supervised baselines. On the GT-graph setting, we see that our method outperforms all recent weakly supervised baselines, and even outperforms fully supervised methods such as iterative message passing and MotifNet. For the contribution of our proposed components on Zarian's split, in terms of recall at 50, the modeling of phrasal context improved 26%. The iterative detection further improved 18%. And our final model with all three components achieved a score of 4.92, which doubles the performance of the basic model. On the CapGraph setting, the absolute performance is worse than that on the GTGraph setting because of the noises in the captions. However, we still see the similar trend. Our components, namely the phrasal, iterative, and sequential modeling, all have positive effects. We show the importance of phrasal and sequential contexts. In the top left example, with the local information of the man, the model without modeling the phrasal context locate to the head region. In comparison, knowing that this is a man on the road wearing a helmet, the phrasal module determines to focus on the whole body of the person. We show the effects of sequential context on the right. Given the plate as the subject and the pizza as the object, the initial result is plate on pizza, which is not making sense. Our module refined it to plate on the pizza, based on its knowledge regarding sequential common sense. In conclusion, we introduced a method that leverages caption supervision for scene graph generation. Captions are noisy, but can be obtained for free. To leverage caption supervision, we proposed to model the phrasal and the sequential contexts and iteratively refine detection scores. We hope our work inspires further studies.